Hello and welcome to the second part of our lecture. On this part we are going to find out expressions for the Fermi level in doped as well as undoped semiconductors. So some important parameters of optoelectronic devices are dependent on the Fermi level. The Fermi level determines the carrier concentration in the conduction and valence band. Expressions for EF can be derived for intrinsic as well as doped semiconductors based on the theory that we have just seen. So for an intrinsic semiconductor we saw that the electron carrier concentration was equal to the hole carrier concentration, which we called Ni. So both these things are equal to Ni, and this was because for every electron that rose up to the conduction band it left behind a hole, and therefore for an intrinsic semiconductor carrier concentrations for electrons and holes have to be the same. Well, if we equate this and use the expressions that we found for N and P before using the Boltzmann approximation, we have this expression right here, right? Nc times e to the power of minus Ec minus Ef over kT is equal to Nv divided by e to the power of minus Ef minus Ev divided by kT. Substituting the expressions for Nc and Nv on this equation right here, so we see that we have Nc multiplying on the left side, Nv multiplying the right side. Therefore, some of the things here are going to cancel out, right? For example, this 4 right here, this 2, the kT to the power 3/2, and also the pi times h bar squared will cancel out, and we'll be left with the effective mass of the electron to the power of 3/2 on the left hand side, and the effective mass of holes raised to the power of 3/2 on the right side. So this is what we are left with, and we can also pass some terms over to the other side, right? For example, on the left hand side we have e to the power of Ec divided by kT in the denominator here, which can pass over to the other side multiplying, so that we have e to the power of plus Ec over kT on this side as well as the e to the power of Ev, which was already there, so we're left with this term. Here we have e to the power of Ef over kT in the denominator. It can pass over to the other side as well, and we'll be left with e to the power of 2Ef over kT because this guy was already there. The effective mass of electrons raised to the power of 3/2 can also pass to the other side in the denominator, and this is what we get as a result. Now the expression we just found was e to the power 2Ef over kT is equal to mh star divided by me star to the power 3/2 plus e to the power of Ev plus Ec divided by kT, right? And we can just take the natural logarithm of both sides here, right? So we get the exponent here, 2 times Ef over kT, equal to the natural logarithm of this term right here, plus, the exponent here as well, so Ev plus Ec divided by kT. And we can simplify further by noticing that since this is the natural logarithm, this can drop down multiplying right here, and if we multiply everything by kT, so multiply across by kT and also divide everything by 2, we finally get an expression for the Fermi level EF. Okay, so EF is equal to 3/4 of kT times the natural log of mh star divided by me star plus Ev plus Ec over 2. Now this term is of the order of a few milli-electron volts, so it's very small compared to this, right, which, you know, EV and EC are of the order of electron volts, and therefore it's gonna turn out that the Fermi level for an intrinsic semiconductor is gonna be around this value here, which is the average between EV and EC, right? So if you have the conduction band edge here and the valence band edge down here, this is going to be exactly halfway between these two, and this is why for an intrinsic semiconductor the Fermi level is halfway between the conduction and the valence band edges, right? Give or take a small term which corresponds to this. Now this was for intrinsic semiconductors, so for doped semiconductors the process is actually simpler. If we take into account the fact that the doping concentration is around 10 to the 12th to 10 to the 19th per centimeter cubed, which is orders of magnitude larger than intrinsic carrier concentration for different semiconductors, which is of the order of 10 to the 8th to 10 to the 10th. And therefore, for example, for an N-type semiconductor, the concentration of electrons is approximately equal to the dopant concentration. So if you dope the material with Nd donor atoms, it's going to have Nd electrons, and in the added to the conduction band, and the carrier concentration for electrons, so the electron carrier concentration can be taken to be equal to the amount of dopants that you introduce. So if Nd is 10 to the 17th, then you can assume that the electron carrier concentration, right, in the conduction band, which is for an N-type semiconductor, is going to be much larger than the whole concentration. So this would be N and this would be P for an N-type. The Fermi level would be way up here, and you can take this to be equal to Nd, right? And if N is known, we can use the expression for itself, for the carrier concentration that we just found, to obtain EF, and this is this expression right here, which we got before. So if this is equal to Nd, right, we can just isolate EF here and we get this. The Fermi level is equal to EC plus KT times Ln of the carrier concentration N divided by Nc, which we know, right? So we just substitute the dopant concentration Nd, be it 10 to the 15th, 10 to the 17th, or 10 to the 19th, we substitute it here and we find EF directly. For a p-type semiconductor, the idea is similar. So the concentration of holes, which are the majority carriers here, is approximately equal to the dopant concentration Na. Right. So in the picture that we've seen before, for a p-type semiconductor, the Fermi level is way down here, and you have carrier concentration for holes which is much larger than the carrier concentration for electrons, because these holes have been introduced on purpose here in the valence band by the introduction, by doping the semiconductor with acceptor impurities. So you can take P, the carrier concentration for holes here, right, which is the area under the curve as we've discussed, to be equal to the amount of acceptor impurities that you've added. So P is going to can be taken to be equal to Na, and if P is known, we can also use the expression for the whole carrier concentration derived using the Boltzmann approximation and isolate EF here, and if you do this, you'll find out that you get EF is equal to EV minus KT times Ln of P divided by NV, where again you can just substitute the acceptor atom concentration introduced in the material in place of P here and find EF directly. So both these expressions were found under the Boltzmann approximation, right? So they, we need to remember that they can be used as long as the doping is not too heavy, as long as EF is not too close, is farther from the band edges than 0.2 electron volts or something to that effect. If this is not the case, if the doping is too heavy, we can use some approximations, some empirical equations that will be better suited in order to obtain the Fermi level energy for this case. So these are the Joyce-Dickson approximation, which is an empirical approximation for EF in this case, right? If the doping is too heavy, we can take for an N-type semiconductor still N approximately equal to the donor atom concentration, the dopant concentration. We can still consider this, and now we can find EF using this empirical equation here. So EF is equal to EC plus KT multiplied by this term inside the square brackets here, which is a function of NC and the electron carrier concentration as well, which we can substitute for the dopant concentration here. For a p-type semiconductor, you have something similar, so you can take p as being equal to the amount of acceptor atoms introduced in the material, and EF is going to be given by this equation now. So EF is equal to EV minus KT times the term inside the square brackets here, right, where P can be substituted by Na, and you can find. So these two are empirical equations that you can use to find the Fermi level if the semiconductor is doped too heavily, as is often the case in optoelectronic devices. Okay guys, so this was it for today's lecture. On our next lecture, we're gonna start talking about PN junctions. So thanks very much for your attention, and I'll see you around.